Is it okay now? Yeah.
Вроде
Uh,
записывается.
Fine. Thank you. So f is a rational function on x if f is defined on an open subset, say U, and the maximal such open subset will be denoted df. Well, sometimes df denotes something else, but maybe we'll survive such notation. Now, we say that f1 equals f2 if they coincide on the intersection u1 intersects with u2, and this is well defined. And then all such functions form a field. It's the field of rational functions. So if x is affine, and A is the ring of regular functions on X, then the field of rational functions on X is just the fraction field of this ring of regular functions. Okay, and also there is a notion of by the way, maybe what I said only had some meaning whatsoever when X was supposed irreducible. So let me add this assumption. Otherwise, say on the coordinate cross, you can have two functions, one vanishing on the horizontal line, another on the vertical line, and their product will be totally zero. Okay, so if I have two irreducible varieties, X and Y, then there is a notion of a rational map or rational morphism. From X to Y. So it's as in the same way as functions. It's not necessarily everywhere defined, but it is must be defined on an open subvariety. So it must be a regular map. Okay, and once again, if two such maps coincide on the intersection of their domains, they are declared equal. And now, if say morphism phi, rational morphism, sorry, is dominant, then it induces the pullback on rational functions. And this is well defined. In fact, if this morphism is not dominant, it also induces some pullback on functions, but it's just identically 0. Okay, so it's not very interesting. Okay, and we'll need the following lemma. That a function, a rational function f on x lies in the image of this pullback morphism from the field of rational functions on y, if and only if the following condition is satisfied. So suppose we have two functions on sorry, two points of x. So there is an open subset u in x, such that if 2 point x1 and x2 lie in this open subset, and phi of x1 equals phi of x2. In particular, this open subset is in the domain of phi. Then necessarily f of x1 equals f of x2. Okay, so for any x1 and x2 in the domain, if they are glued by this morphism phi, then the values of function f are the same. So it looks very natural, and in one direction lemma 1 is evident, but in another direction it is not evident at all, but proved, say, in Shafarevich somehow by induction in the transcendence degree of x, or say the field of rational functions at x over the field of rational functions on y. And even somehow to begin with, if this degree is 0, so the field of functions on x is an algebraic finite extension of field of functions on y, then it's still not very evident. Okay, so we will not prove this lemma. Just refer to basic algebraic geometry.
Здесь нужна доминантность, да?
Oh yes. Otherwise, if the morphism is not dominant, then the induced map on the level of fields is just 0, right? Because the image of x is then contained in some closed subset of y, and the generic the generic functions will vanish restricted there. Okay. So now let me formulate this theorem of Maxwell-Rosenlicht I announced last time, and then let me prove it. So we have an action of G on an irreducible variety X. And hence we obtain the action on the field of rational functions by field automorphisms. And we can take the field of invariance. Okay, and we now the theorem says that we can find an open x prime in X that is G invariant. And also some functions, f1 and so on, fk, invariant functions on X prime. Sorry. G invariant, such that for any 2 points, x1 and x2 in X prime, their orbits coincide, G x1 equals G x2, if and only if f I of x1 equals fi of x2 for all these functions. Okay. Then so we will start proving this theorem. It will be a rather long proof, but before we even prove it,
may I ask a question?
Yes, certainly.
Does this function belong to the polynomial ring of x prime invariant or x invariant?
So these functions are they are rational functions on X, and each of them has its own domain. So it has poles on some divisor or whatever, and there are finitely many of these functions. So you can intersect all their domains, and you obtain an open subset. This is X prime, and they're on X prime. They are regular. Okay, so they are rational functions on X, but regular on X prime. Did I answer your question, or did I?
Yes.
Oh, okay, thank you. So say remark. These functions f1 and so on, fk, generate the field of rational functions on X. Indeed. Let's consider the ring that they generate.
Do they generate all the field, or only its G invariant part?
Oh, sorry, G invariant. Thank you. Thank you. So let's consider the ring that they generate, and say Y will be the spectrum of this ring, and phi from X prime to Y, the induced natural morphism. Okay. So now let's take any function f, a rational function, invariant under G. So then by the theorem of Rosenlicht, we have if phi of x1 equals phi of x2, then the orbits coincide. And then it follows that f of x1 equals f of x2. So here x1 and x2 lie in x prime and the domain of function f. Okay, and so by lemma 1, we conclude that f lies in the fraction field of A. Okay, so now let's try to prove this theorem of Rosenlicht, and the proof will be rather long. It will consist of 6 steps, and somehow we will reduce our general situation to some more and more favorable situation. So step 1. I mean, all the reductions are just shrinking of x, because it is a statement about the field of rational functions on x. So if we replace x by an open subset, then we'll lose nothing, and that's what we're going to do. So first of all, we reduce that is shrink x to the case when all the orbits have the same dimension.
Миша, прости, что мы редуцируем? Что такое shrink x?
So here is the theorem of Rosenlicht, and as you see, it is a statement about rational functions on x. Yeah. So we can replace x by an arbitrary open subset of x. Yes. Then the claim of theory will not change. So we are allowed to throw away as many closed subsets as we want. Okay. And by shrinking, I mean passing to an open subset, a smaller open subset. Okay.
Хорошо.
And so first of all, I claim that after passing to certainly G invariant open subset, we can make sure that all the G orbits have the same dimension. So shrink means replace x by G invariant open subset. Okay. So I claim that the set of points x such that the dimension of their G orbit is less than whatever d is closed in x. Okay, and this is because for any family, that is the fibers of an algebraic morphism, the dimension can only jump under specialization. And by the way, let me formulate a small aside. For this reason, the orbit, the G orbit, cannot form an algebraic family. So there is no morphism. Say phi from X to Y, such that the fibers are exactly G orbits. Well, certainly, we in fact we proved that this is so for finite group G, right? But if G has dimension bigger than 0, so it's not finite, then it's impossible.
Sorry,
Yes.
Why the subset of X, which is an big S such that dimension is less than D, is not all X?
No, I mean sometimes it is, but I mean for any D, right? So it depends. It may happen that from the very beginning, all the orbits have the same dimension. Then this statement is vacuous. But say like in the adjoint action of GLN on the matrices and by n matrices, the generic orbit has dimension n, right? Over a regular matrix
Okay.
has an orbit of dimension n. But say any central matrix, scalar matrix, say 0 matrix, has an orbit, just a point orbit, so its dimension is 0. Okay, but then the orbits of dimension less than 1, 0-dimensional orbits, they do form a closed subset, right? The scalar matrices. Then there are also the orbits of dimension less than 2. They also form a bigger closed subset, and so on. Okay, and then if we remove all those orbits, we are left with the orbits of dimension exactly n, and they form the complementary open subset. Okay, so that's what goes on.
Okay.
So once again, the orbits cannot form fibers of any family for this reason. For example, just in this adjoint action of GLN on its Lie algebra, we see that the orbits cannot form an algebraic family, but the condition of being stabilizer of a point, it is a closed condition. Yes, so we can form the following subvariety: S inside G times X. So this S is the set of points Gx, such that Gx is X. Okay, the universal stabilizer, so to say, and certainly it projects onto X. Okay, and the fibers of this projection are the closed subvarieties in G, the stabilizers, and the dimension of stabilizers can only jump by this algebraic geometric fact. Okay, so the dimension of orbits can only drop. Okay, so the step 1 is proved. Okay, so we replace X by this open subset. So it's G invariant, open, and in U, any G orbit has dimension equal to d, and hence
So,
yes.
so for this, we have to use a basic fact that dimensions of orbits and stabilizers are complementary in the
Also,
dimension of group.
yes, thank you. Absolutely. So after this, we conclude that in this open G invariant subset U, all the orbits have the same dimension d. In particular, they are all closed. Right? Because if it's not closed, then in its closure, there must be some smaller orbit, but it's impossible because all the orbits have the same dimension. Fine. This was our first reduction step.
Sorry, and I have a question.
Yes.
Maybe you told this on the previous lecture, but I can't remember. Why Jx is a subvariety?
No, somehow we didn't prove this, and it is not evident at all. I will maybe comment on it somewhat later in the course. I mean, maybe next week. But somehow we have to use some structure theory of algebraic groups. And last time we started some introduction to this structure theory, but we'll continue next time also. But then at some point I will have to stop, unfortunately, because as far as I understand, Vadim Vologodsky will give a course on algebraic groups next year, and I just and I don't want to, and I can't just copy this course here and now. Okay, so I will refer to some basic facts in algebraic groups and use them. Okay. So the second step is about the graph gamma of the G action, and by definition, gamma is the set of points x1 and x2 such that there is G such that gx1 equals x2, or equivalently gx1 equals gx2. So they lie in the same orbit. Okay, and I don't know. Well, somehow maybe it's not a very best name. I mean the graph, but this is the standard name, so we'll use it. It's not a graph of any morphism, but it is called the graph of G action. Okay, and so the next step will be shrinking of x. X again will be replaced to some G invariant open subset, where the graph gamma will be closed. Okay, and in general, if gamma is closed, then you immediately see just by intersection with fibers that all the orbits are closed. And this is our standing assumption at the moment, right? We already reduced to the case when all the orbits are closed. but unfortunately, the converse is not true. So let's consider a counterexample. When all the G orbits are closed, but gamma is not closed. So in this counterexample, G will be the multiplicative group, the simplest possible, not finite group, and X will be just two-dimensional plane, but without the origin. And the action will be the hyperbolic action. So say lambda x y will be lambda x lambda inverse y. Okay, so the orbits are the hyperbolas like this, and also the punctured lines, okay, and also the vertical punctured line. And if we had not removed the origin, then these punctured lines would not be closed orbits. But since the origin is removed, all these orbits are closed. Okay, so the origin is removed, and now the graph gamma is obtained from the closed subvariety in A2 without 0 times A2 without 0 with coordinates x1, x2, y1, y2. So given by equation x1, x2 equals y1, y2. So this is closed, but gamma is obtained from this removing the planes x1 equals y2 equals 0 and x2 equals y1 equals 0. Okay. So once again, though we already know that all the orbits are closed, still the graph is not necessarily closed, and now we are further shrinking our x to guarantee that the graph is closed. Okay, so let's do this. Okay, so the graph is not necessarily closed and not even how so to say locally closed. We only know that the graph is the image of some subvariety, so it's constructible. So gamma in x times x is the image of an algebraic morphism say phi. I hope it's still not overused. G times x to x times x, namely phi of g and x equals x and gx. Okay, and so by Chevalier theorem, gamma is constructible. And hence it contains a subset U that is locally closed in X, and it is sort of almost open in gamma, so that gamma lies in the closure of U. Okay. So the closure of U is closed, and gamma is I don't know what to say. Is big there. Okay, not necessarily closed, but almost closed. Gamma is almost the closure of U. Anyway, we can say that gamma lies in the closure of gamma, and this closure of gamma is already equal to the closure of U. This is a closed subvariety in X. Okay, and now this is G times G invariant subvariety in X times X, and let us replace U by G times G applied to U, and so we can assume that U is G times G invariant. Okay. Now consider the first projection. P1 from the closure of U, that is the closure of gamma, to X. And then we claim that the projection of the boundary of U is not dense in X. Oops, sorry. Okay. So I will prove this claim momentarily, but assuming this claim, we can replace X by X naught. That is the complement to this the closure of this projection. Okay, so it was not dense. So this complement is not empty, an open subset. Okay, and now the intersection of gamma with X naught times X naught is already closed. And certainly this X naught is G invariant. Okay, so this is the desired shrinking, this X naught. we only have to prove this claim that the projection of the boundary is not dense. Okay. And this is done just by comparing dimensions. So what can we say? Yes, yes.
А можете быстро вернуть на предыдущую страничку? Я просто забыла, что мы хотим.
Yes. So what's the question?
Просто хочется держать в голове утверждение, которое мы так долго доказывали.
Right. We're proving that that we can shrink our x so that the graph of the action will be closed.
Спасибо. Спасибо.
For example, in this counterexample, we have to remove the coordinate lines, right? When x, the first or second coordinates vanish, then we are only left with hyperbolas, and the graph of these hyperbolas, it is closed. Okay. Pardon me. Okay. So it remains to prove the claim, namely that the boundary of this open U is not very big. Yeah, that is projection. It cannot be dense in X. So let's prove it by reduction to absurd. So assume that.
Yes? Почему гамма замкнута в этом пересечении с иксом?
Just because gamma bar is U bar, and I don't know what to say. What else to say?
Okay.
Just because gamma bar is U bar. I don't know. Maybe it's easier to understand by yourself than if I try to verbalize it. Okay. So once again, assume this projection is dense. Oops. Okay. Then if X lies in the projection of this U, then the intersection of U with the fiber over X is this point X times the orbit, and right, we assume that U was G times G invariant. Okay, and hence the dimension of intersection is D, and hence what I want to say. The dimension of this is D, and hence the dimension of the whole graph is also D, right? Sorry, D plus dimension of a plus dimension of There's one. Sorry, I'm confused. Um, uh, mm, mm, mm. Okay. Sorry. So mm, the mm, I say this. Maybe not this way. The uh, uh, let me say it once again. Okay. So mm, so any fiber of P1 intersected with our graph has dimension. It is just the orbit. So has dimension exactly d. Okay. So if u bar minus u is dense in X, then the dimension of u bar minus u is at least d plus dimension of X, right? Because in the base we have some dense subset which has dimension at least dimension of X, and in the fiber we also have we have dimension d, right, as the dimension of orbit. Okay. So because the intersection of pp1 inverse of X with gamma is just gx, and so the dimension is exactly d. Okay. On the other hand, for u, we have the opposite estimate. The dimension of u itself, yeah, the boundary had dimension d plus dimension of X, and u itself also has dimension not bigger than d plus dimension of X. Again, we consider the fibers mm, have dimension exactly D. Okay? So we get that the dimension of the boundary is bigger or equal than to dimension of U. This contradiction. Okay. So we proved the claim, and from the claim also our desired reduction follows. Okay. So now we can go to the next step 3, and we already know that all the orbits have the same dimension, and they are closed. And moreover, the graph of the action is also closed. Okay. Now, since it is closed, it is given by some equation, and we're going to use this. So we take an open affine y in X, but now, contrary to what we achieved before, this open affine y is not necessarily G invariant. So it cannot be taken G invariant. For example, suppose that X is projective line P1 and is acted upon by GL2. But then the action is homogeneous. So you cannot find any G invariant affine subvariety. Any G invariant subvariety must coincide with the whole P1. Okay. So we take not G invariant open affine subvariety Y, and I is the ideal of the closed intersection gamma with the square of Y. Okay, so it's an ideal in the ring of functions. Okay, and now there is no action of G on Y, but there is a rational action of G on Y, right? Because rationally Y coincides with X, and we're going to use this. So we consider this field of fraction K, rational functions of on X. It coincides with the field of rational functions on Y, and consider a K algebra, K of Y okay. So in this tensor product of ring of functions C of Y with C of Y, we localized in the first variable, right? We allowed all the fractions in the first variable. And now J is the ideal in this algebra generated by I. Okay, so the I was ideal in the tensor product of regular functions on Y, and now we'll localize in the first variable. Okay, now the group G, sorry. sorry. For some reason, I cannot write anymore. Don't know why. Maybe somebody has an idea why cannot I write anything else apart from general idiotism?
Может, попробуй теперь зайти в приложение, то есть выйти на главный экран, а потом.
Mm, mm, okay.
Вот
Okay,
вот
so
этот кружочек
pardon me?
вот
Pardon me?
этот кружочек снизу нажать.
Mm, mhm. Just let me see what I have already. Okay, let me try now once again. Oh, now it works. Sorry about this. Okay, so J is this partially fractional ideal, so to say, and now the group G acts on this strange algebra via its action on K, just via the first variable. Okay, as we argued, it does not act on Y, but it acts on only on the field of fractions, on the rational functions of Y, and now clearly this J is G invariant. Okay, and then our next step will be that J is generated by G invariant elements. Okay, and this will be already almost the victory. I mean, more or less, these elements will be, or their coordinates, so to say, will be the generators we're after. I mean, the generators in Rosenlich's theory. So the fact that this ideal is generated by the G-invariant elements has nothing to do with any specifics of our algebraic geometric situation. It's a very, very general fact. So let me formulate this general fact on the next page. So this general fact is as follows. So we have a vector space V over our field K, and in fact, this V will be. Sorry, it's not over K. It's over the invariance invariance of G in K, and this vector space will be Kg of Y. Okay, and we have a G invariant vector subspace and now K vector subspace in, say, V naught inside the extension of scalars. Okay, and this V naught will be our ideal J. Okay, And then the general fact is that this G invariant subspace is necessarily generated by G invariant elements.
So by general, you mean that G is now just an abstract group?
G is an abstract group, K is an abstract field, everything is absolutely abstract. So it has no nothing to do with its origin in algebraic geometry. Okay, this is a general fact about actions of group on fields and vector spaces. Okay, we are not interested in the origin of anything here anymore. So it's always generated by G invariant vectors. Okay, so let's prove it. We reduce to the case when there are no invariants. Reduce just replacing V by a complement V prime to the invariant, okay, and replacing V naught by the intersection. Okay, and so now after this we have to prove that if there are no invariants, then V naught is necessarily 0. Okay, and how do we prove this? Take some vector, non-zero vector, and just write it as V equals sum of AI tensor VI. So AI are elements of our field, and VI are elements in the vector space V. And we assume that this is a minimal minimal such decomposition. So n is minimal. Okay. And now just by rescaling, say A1 may be assumed to be 1, but then GV minus V is well, has a similar expression, but with n minus 1 summands. So it must be E0. So V must be invariant, but we know that there are no invariants. Okay. Okay, so this general fact is proved, and what did we need it for? To prove that the ideal J is generated by G invariant elements. Okay, now we know this. Fine, so we can go to the next step. 5. And we know that Y was a fine algebraic variety, so the ring of functions on it is Noetherian. And in particular, the among the G invariant generators of our ideal J, we can choose finitely many generators, say F1 and so on, FL. And let's write them as follows. Fi is the sum of Fij tensor Hij, the sum over J. So here Fij are G invariant elements of the field, and Hij are regular functions on Y. Okay. And there we are. These functions Fij are exactly the Rosenlicht function. So it's the end of the proof, the last step 6. So the Fij's are the desired Rosenlicht generators. Indeed, we can shrink Y so that all these Fij's are now regular. Okay, so we replace Y by a smaller open subset. And then it means that F1 and so on, FL lie in the ideal, in the regular ideal, not in the ideal J that was localized over the first variable, but in the regular ideal lies in C of Y times Y. Okay, and they generate this ideal. Okay. So now let's take 2 points in the graph, y1, y2 in the graph, but intersect with y squared. Then this intersection is exactly the zero set of the ideal I. Okay. Maybe not take, but let me say the 2 points are in the ideal if and only if all the functions vanish on this pair. Okay, but now, since we have the composition of those fi's, it is equivalent to the fact that Fij of y1 times Hij of y2 is 0 for any I. And so if Fij of y1 equals Fij of, sorry, maybe, no, y2, but maybe, or some other y1 prime, then by definition of this ideal, we have the pair y1 y2 lies in the graph if y1 prime y2 lies in the graph, and this is equivalent to gy1 equal gy2 equal gy1 prime. In particular, gy1 equals gy1 prime. They are in the same orbit. Okay, fine. So we're almost done. Just take x prime is the saturation of y. So as I explained, it may be not an affine subvariety, but never mind. It is an open and G-invariant subvariety. In X, and if Fij of x1 equals Fij of x2 for any ij, but the orbits are different, then take y1 in the intersection of this orbit with y, and y2 in the intersection of the second orbit with y, and well, there's a contradiction. Okay, so if Fij of x1 equals Fij of x2, then necessarily the orbits coincide. And this is the claim of Rosenlicht's theory. There we are. Let me just formulate a corollary. Of this theorem, that the transcendence degree of the field of invariant rational functions is the dimension of x minus this dimension of general orbits D. Or
I'm sorry, transcendence degree over what?
over complex numbers. Yeah, just the well, sort of it's one of definitions of dimension in the favorable cases. Okay, and in particular, if this transcendence degree is 0, then the field of invariant functions is just complex numbers, and this happens only if X has well, necessarily unique, open, dense orbit. Okay. And well, this is an immediate corollary of the theorem, and well, maybe let me try to scroll back. Yeah, here. You see that there was this remark about these Rosenlicht functions generating the field. Okay, so from this we immediately see the corollary. Okay. Okay, so here we are, and the time is up. So next time we'll continue with some basics of structure theory of algebraic groups, and maybe the whole next week we'll do this, and then we'll move to some more advanced invariant theory topics. Okay, so are there any questions? If not, then see you on Thursday. I will send you the new home assignment, and the old home assignment is due today.
Sorry, I have
Yes.
a question.
Yes.
How the deal is going to be if we, for example, would like to work with not closed points, or maybe not only algebraically closed field C, for example, with some points on R, like, or even FP.
But what is the question? So what happens if the base field is not algebraically closed?
There is
So
two
what is the
questions. Yes. First, what is the можно я по-русски? Ну, допустим, если у нас поле алгебраически не замкнуто, нет, допустим, вот у нас поле просто какое-то алгебраически замкнутое, то у нас ничего не меняется в наших доказательствах.
So your field is algebraically closed or not? I didn't hear.
Ну, я имею в виду, что, например, если мы...
Like FP bar or what?
Ну да, например, FP bar. Там что-нибудь меняется или нет?
So far not, but later on in the course, first of all, we will use analytic methods. So for example, we'll use maximal compact subgroups very much. So this does not work over FP bar, and also many statements fail in finite characteristic. especially those related to Lie algebras. So next week we'll introduce the notion of Lie algebras, and it works over complex numbers in a very different way to the one in finite characteristic.
Вот, да, второй вопрос, чего делать с алгебраически незамкнутыми полями? Ну, то есть можно рассмотреть просто пример, когда R, там, ну, иногда не выходить в комплексные числа, наверное. Вот. Там сильно все меняется или не очень?
I don't even know what
Может быть, вы просто не знаете. Я просто интересуюсь, может быть, все нормально.
Maybe you can formulate some concrete question, like certainly the situation is different, but what maybe if you have some particular question, I can try to answer it, but otherwise,
ну, например,
I don't know what to say.
Мы берем, определяем точки и смотрим на орбиту точки, то в данном случае нам нужно будет, вообще можем ли мы рассматривать орбиту точки, если поле...
Certainly we can, but well, I don't know. For example, there is an important theorem that all the Cartan subgroups are conjugate. We'll discuss it soon. But it's only true over complex numbers, but not true over real numbers.
Ну да, а вот эта вот теорема Розенлихта,
yes.
Розенлихта, мы в ней тоже сильно использовали алгебраическую замкнутость, или можно похожее поведение сформулировать для незамкнутого поля?
Мне кажется, можно просто взять это утверждение, потом еще взять инвариант сильно группы Галуа в самом конце, а до этого работать над C.
Нет смысла.
So the claim is just you want to have just literally the same claim.
No, I have a plausible conjecture that Galois norms of Rosenlicht generators will be Rosenlicht generators in an appropriate sense.
I found this question on Math Overflow, and it's indeed true of an arbitrary field.
Okay, Rosenlicht theorem is true over arbitrary field. Yeah, that's what you say.
Yeah, I guess so.
Great, thank you.
А вот в теореме Розенлихта есть какая-то оценка на количество этих разделяющих функций? Мне почему-то казалось, кажется, что была, нет?
But in what terms?
Ну, не знаю, там размерность группы, многообразие.
No. How do you mean? No, absolutely. Just in Hilbert Bayes' theorem, there is no such estimate.
Хорошо.
No, so there's at least I don't know any effective estimate on the number of generators. For example, in this very in the very first home assignment with finite subgroups of SL2, the fact that it's enough to have 3 generators is not very evident. Well, it's true just by inspection that 3 generators always suffices, but there is no a priori estimate like this.
Ладно, спасибо.
So if you know that the quotient is smooth, then like in Chevalier theorem, then it's evident. But otherwise, there is no a priori estimate that I know of. Okay, so if there are no more questions,
I have a question.
Yes.
First of all, you mentioned today some theorem from Shafarevich. I wanted to ask you where approximately, more exactly, where is it stated and proved in the book?
Okay.
К сожалению, мне нужно идти, поэтому я запись, наверное, останавливаю.
Fine. Yes, absolutely. Thank you.